Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
Mirage and looming. The refractive index of air increases with its density. In hot places, air near the ground is hotter than air at a height. Hot air is less dense. Hence, in still air the refractive index of air increases with height. Because of this, the light from tall objects like a tree try to pass through a medium whose refractive index decreases towards the ground. Hence, the ray of light successively deviates away from the normal at different layers of air and undergoes total internal reflection when the angle of incidence near the ground exceeds the critical angle. This gives an illusion as if the light comes from somewhere below the ground. Because of the shaky nature of the layers of air, the observer feels as if the object is getting reflected by a pool of water, or wet surface beneath the object as shown in Figure 6.23a. This phenomenon is called mirage. In the cold places the refractive index increases towards the ground because the temperature of air close to the ground is lesser than the temperature at a height above the surface of Earth. Thus, the density and refractive index of air close to the ground is greater than for air at a height. In the cold regions like glaciers and frozen lakes, the reverse effect of mirage will happen. Hence, an inverted image is formed little above the surface as shown in Figure 6.23b. This phenomenon is called looming. It is also called a superior mirage, towering and stooping. 6.4.
These two diagrams explain the phenomena of mirage and looming. In this case, the hot air above the surface of the earth will be present, and that will be a rarer medium, and as the height increases the medium becomes denser and denser, and therefore the rays will appear to come from the surface of the earth. And this is the phenomenon of looming, which is taking place in the colder regions. In this case, the air above the surface of the earth will be denser, and as the height increases the medium becomes rarer and rarer, and therefore the objects on the surface of the earth will appear to come from a certain height.
7.3 Prisms making using of total internal reflection. Prisms can be designed to reflect light by 90°, or by 180° by making use of total internal reflection as shown in Figure 6.24a and 6.24b. 45 degrees B, 45 degrees B, 45 degrees A, 90 degrees A, 90 degrees, 45 degrees B, 45 degrees A, B, A, B. In the first two cases, the critical angle IC for the material of the prism must be less than 45°. Prism in Figure 6.24b inverts the object on the same side. Prism in Figure 6.24c inverts the object on the other side. 6.4.7.4 Radius of illumination, Snell's window, Figure 6.25 Light source inside water tank. When a source of light like electric bulb is kept inside a water tank, the light from the source travels in all direction inside the water. The light that is incident on the water surface at an angle less than the critical angle will undergo refraction and emerge out from the water. The light incident at an angle greater than critical angle will undergo total internal reflection. The light falling particularly at critical angle graces the surface. Thus, the entire surface of water appears illuminated when seen from outside as shown in Figure 6.25. On the other hand, when the light entering the water from outside is seen from inside the water, the view is restricted to a particular angle equal to the critical angle. IC. The restricted illuminated circular area is called Snell's window as shown in Figure 6.26, a. The Figure 6.26, b, shows the angle of view for water animals.
This diagram shows the Snell's window in case of underground illumination, and this diagram shows the angle of view for water animals. This is critical angle, this IC, and this fish can see the tree like this, and on this side it will be like this.
The angle of view for water animals is restricted to twice the critical angle 2IC. The critical angle for water is 48.60. Thus the angle of view is 97.20. The radius r of the circular area depends on the depth d from which it is seen and also the refractive index n of the medium. The radius r of Snell's window can be deduced with the illustration as shown in Figure 6.27. RICICB-CN1DA12_physics_vol2_unit 6. It is seen from a pointer at a depth d. The Snell's law in product form, equation 6.19, for the refraction happening at the point B on the boundary between the two. RDN equals
The Snell's law in the product form is given as N1 sin IC equal to N2 sin 90 degrees, and N1 sin IC is equal to N2 since sin 90 degrees is equal to 1, and therefore sin IC can be written as N2 by N1. From the right angle triangle ABC, you can have this equation as sin IC is equal to CB by AB, that's equal to R by root of D square plus R square, and equating the above equations, we have R by root of D square plus R square is equal to N2 by N1. And squaring on both sides, we have R square by R square plus D square, and that's equal to N2 by N1 the whole square. And taking reciprocal, we have this equation, and on simplifying, we have this equation, and taking reciprocal and rearranging, we will get the equation as R square equal to D square N2 square by N1 square minus N2 square, and taking square root, we have this equation 6.35 such as, that is R is equal to D into root of N2 square by N1 square minus N2 square. If the rare medium outside is air, then N2 will be equal to 1, and we can take N1 is equal to N, and therefore the radius of Snell's window, that is called as the radius of the Snell's window, radius of illumination, and that is given by this expression R is equal to D into root of 1 by, that is into D into 1 by root of N square minus 1, and this equation can be written as R equal to D by root of N square minus 1.